Welcome again to our online class, and today I'll be with you in solving telecommunication questions. So let us start with example number 1. So example number 1 states that a carrier wave of frequency 10 MHz and peak value of 10 voltage is amplitude modulated by a 5 kHz sine wave of amplitude 6 voltage. Determine the modulation factor, sideband frequencies, amplitude of sideband components, and you are told to draw the frequency spectrum curve. So let us solve this question. Modulation factor MA is equal to ES over AC. So back to our question, we have a carrier wave of frequency 10 MHz. So this one is the frequency of a carrier wave and the peak value of 10 voltage. This one is the amplitude of a carrier wave. Is amplitude modulated by a 5 kHz sine wave of amplitude 6 voltage. So 6 voltage is the amplitude of a signal wave, or EAC. So the amplitude of a carrier wave, or EC, is 10 voltage. So we're going to plug the values. So it will be equals to ES, which is 6 voltage, over EC, which is 10 voltage, which will be equals to 0.60. So this one was Roman 1. And Roman 2, you are told to determine the sideband frequencies. So sideband frequency, we have two sideband frequencies. We have the upper sideband frequency and we have the lower sideband frequency. So we are starting with the lower sideband frequency. So the formula for lower sideband frequency equals to FC minus Fs, or frequency of a carrier wave, then minus frequency of a signal wave, which will be equals to 10,000 kilohertz minus 5 kilohertz. So remember here, you have the frequency of a carrier wave, 10 megahertz. This 10 megahertz, we convert it into kilohertz. If you convert 10 megahertz into kilohertz, you're going to get 10,000 kilohertz. So if you subtract 10,000 kilohertz minus 5 kilohertz, we get 995 kilohertz. So this one is a lower sideband frequency. Let us now find the upper sideband frequency. So upper sideband frequency, which is FC plus Fs, will be equals to 10,000, then we plus 5 kilohertz, which will be 10,005 kilohertz. So now we have the sideband frequencies. We have the upper sideband frequency and we have the lower sideband frequency. And lower 3, let us now find the amplitude of sideband components. So amplitude of sideband component, it will be equals to MA. MAEC you divide by 2. But MA is modulation factor, and we have already calculated the modulation factor in A, which is 0.6. So we're going to substitute MA, which is 0.60, then times 10. 10 is EC, then we divide by 2. So 0.6 times 10 is 3. If you do 0.6 times 10 is 60. If you divide by 2, you're going to get 3. So now we have the amplitude of the sidebands. We have the sideband frequencies. The next step, or Roman 4, we're going to draw the frequency spectrum curve. So drawing the frequency spectrum curve, we're going to have the x-axis and we're going to have the y-axis. In the x-axis, we're going to have the frequency in kilohertz, but in the y-axis, we're going to have the amplitude in terms of voltage. So this one will be the frequency of the carrier wave, or FC, which will be 10,000. We've already been given here 10 megahertz is the frequency of the carrier wave. If you convert 10 megahertz into kilohertz, it will be 10,000 kilohertz. But the amplitude, it was 10 voltage. So I'm going to put here 10 voltage. So let us now draw the sidebands. We're going to draw the lower sideband and the upper sideband. So starting with the lower sideband, we're going to draw its frequency, which is 995 kilohertz. But the upper sideband frequency is 10,005 kilohertz. 10,005 kilohertz. But the amplitude is 3 voltage. And up to here, you have already drawn the frequency spectrum curve. So you can see it starts 9995 kilohertz, then 10,000 kilohertz, then 10,005 kilohertz. It is going in terms of increasing order. So this one is a frequency spectrum. And just to remind you, these questions are very, very common. You'll be given a question, you'll be required to calculate the sideband frequency, and at the end, you'll be told to draw the frequency spectrum curve. Example number 2 says that explain the terms of amplitude modulation and bandwidth. That is A. So going back to our notes, to our previous class, we have already explained the term amplitude modulation and bandwidth. We said amplitude modulation is a type of modulation whereby the amplitude of a carrier wave is changed according to the intensity of a signal wave. Coming to the bandwidth, we said bandwidth is a range of frequency. So you can go back to the previous class and you can remind yourself in these terminologies. So let us calculate question B. Question B says, what is a bandwidth when the frequency is a range of 500 Hz to 3500 Hz amplitude modulated? So coming to the bandwidth, it has a formula which says that 2 times highest frequency. So we have been given here a range of frequency. We have been given a range of frequency from 500 Hz to 3500 Hz. So the highest frequency in the range is 3500 Hz, and this one will be required to calculate the bandwidth. So bandwidth will be equals to 2 times 3500, which will be equals to 7000 Hz, and this one is a bandwidth. Coming to the example number 3. Example number 3 says that the carrier of frequency 800 kHz is amplitude modulated by a frequency ranging from 1 kHz to 10 kHz. What frequency range does each sideband cover? So this question is a bit of different from the previous question because you have the carrier frequency which is 800 kHz, but also you have the signal frequency which they are in terms of a range. So the frequency of a signal wave are given in terms of a range from 1 kHz to 10 kHz. In the previous question, the frequency of a signal wave were not in terms of a range. Now, let us calculate the upper sideband frequency and the lower sideband frequency. So coming to the lower sideband frequency, we know lower sideband frequency is Fc minus Fs. But here we have F1 which is 1 kHz and F2 which is 10 kHz. So they are given in terms of a range from 1 kHz to 10 kHz. So what we are going to do here, we are going to subtract both 1 kHz and 10 kHz from 800 kHz. So Fc minus F1, which will be equal to 800 kHz minus 1 kHz, which is 799 kHz. This one is a first lower sideband frequency. So the first lower sideband frequency is determined by taking Fc minus F1, which you're going to get 799 kHz. So another lower sideband will be taken by taking Fc minus F2. So it will be determined by taking Fc minus F2. So it will be Fc minus F2, which is equal to 800 kHz minus 10 kHz, which is equal to 790 kHz. So also the lower sideband will be in terms of range. It will be ranging from 790 kHz to 799 kHz. So let us now calculate the upper sideband frequency. It will be the same. It will be Fc plus F1, which will be equals to 800 plus 1 kHz, which will be equals to 801 kHz. So this one is the first upper sideband frequency. So there will be also the second upper sideband frequency, which will be by taking Fc plus F2. So it will be Fc plus F2, which equals to 800 kilohertz plus 1 plus 10 kilohertz, which is equal to 810 kilohertz. So to summarize now, the frequency range in the lower sideband is from 790 kilohertz to 799 kilohertz. From 790 kilohertz to 799 kilohertz. And the frequency range in the upper sideband, will be from 801 kilohertz to 810 kilohertz. This is the frequency range in the upper sideband. So from this data, we can now draw the frequency spectrum curve. So as we know, frequency spectrum curve, it has x-axis, y-axis, but here now they will be in terms of ranges, the lower sideband and the upper sideband. So this one is a line for the frequency of a carrier wave, which the frequency of a carrier wave is 800 kilohertz. So it will be 800 kilohertz, but also we're going to draw frequency of the lower sideband, which is in terms of range. So it is from 790 kilohertz to 799 kilohertz. We're going to shade, but also we're going to draw the upper sideband frequency, which is also in terms of a range, which is from 801 to the 810 kilohertz. We're going to shade. And up to this point, you have drawn the frequency spectrum of this question. I hope you have seen the difference of drawing frequency spectrum of this question and frequency spectrum of the previous question. These questions are very, very common. You will see them in your mock exams, and you will see them in your next exams, to your school exams. They are very common. Expect to see them. Let us now see example number 4. So example number 4 says that a carrier wave of 500 watts is subjected to 100% amplitude modulation. Determine power in sidebands. And Roman 2, determine power of the modulated wave. So let us solve this question. We know power in sidebands is given by MAEC squared, then divided by 4R, because we have the two sidebands. But power of the carrier wave is given by EC squared divided by 2R. So we're going to substitute this power of carrier wave to the power of sidebands. So power of sidebands will be equals to power of carrier wave times MA over 2. So this EC squared over 4R has been substituted by EC squared over 2R. Then by 2, it remains 2. R and R they cancel. EC squared and EC squared they cancel. So it will be MA over 2 times power of the carrier wave. Because we have done this because we have the power of the carrier wave, which is 500 watts. And we have been told it is subjected to 100% amplitude modulation. So this one is the modulation factor. 100% modulation, this means the modulation factor is equal to 1. If it was 80%, modulation factor was 0.8. If it was 50%, then the modulation factor could be 0.5. 20%, 0.2. So if it is 100% modulation, amplitude modulation, the modulation factor will be equals to 1. So power of the carrier wave we have, it is 500 watts. We're going to substitute. So power of the sideband will be equals to 500 watts, then times MA, which is 1, then you divide by 2. So the answer here will be equals to 250 watts. This one is the power of sideband. Coming to the power of the modulated wave is equals to power of sideband, then you add power of the carrier wave. That is the formula for finding total power of the wave or power of the modulated wave. So it will be equals to 250 plus 500 watts. If you add, you will get 750 watts. Let us see another example from NECTA 2019. So we had a question here, which was question number 3, Roman 1. identify the 3 basic elements of communication system, you are going to be awarded 3 marks. Going back to our previous class, we said the 3 basic elements of communication system. We had the transmitter, communication channel, and the receiver. So if you are passed through the previous questions, if you are passed through the previous class, I hope you are very conversant with this question. So Roman 2, the question was asking why skywaves are not used for transmission of TV signals. So we're going to be awarded 2 marks. So skywaves, as we said to our previous class, the signals is transmitted from the transmitter to the receiver, but before reaching the receiver, it first will be reflected by the ionosphere. So from the transmitter, the wave will be reflected by the ionosphere, then it will reach the receiver after being reflected. But the TV signals, they have a very high frequency. They have a high frequency. So simply the TV signal, they can penetrate the ionosphere. So the best way to transmit TV signals is by using satellite communication. Simply because TV signals or the TV signal waves, they can penetrate the ionosphere. They can be reflected by the ionosphere to reach the receiver from the transmitter. So I think here there is the answer. The television signals, they have a frequency in 1000 to 200 megahertz range. So skywaves cannot be used in transmitting TV signals having frequency more than 80 megahertz, because these waves are not reflected back by the ionosphere and penetrating to the outer space. So it is just the same as I explained, because TV signals, they have a very high frequency ranging from 100 to 200 megahertz. So it is easy for them to penetrate the ionosphere and go to the outer space. So skywave is not suitable for TV transmission. So question number 13b, you are given a diagram, a figure, which was a diagram of a transmitter with its components. Then the question was asking you to write the role of each component, which was labeled A, B, C, D, E, and F4. So starting with A was microphone. And we said microphone is a transducer, converting one form of energy to another form of energy. So a microphone simply converts a sound energy into electrical energy. And B was amplifier for raising the strength of the electrical signal from the microphone. And C was the modulator for doing superimposition of a high energy carrier wave with a signal wave from the amplifier. But D was an oscillator. Oscillator simply, its function is to produce a high energy carrier wave which will be used during superimposition in a modulation process. But E, it was a transmitting antenna. It converts the electrical signal into electromagnetic wave for being transmitted. You can go back to our notes. You can go back to our class. I think I explained these components clearly. Again, another example was Nectar 2017. Question number 11, it was paper 1. So question number 11, C, Roman 1. You are asked to list 3 basic elements of communication system. I think this question is very simple, and we have already listed them in the previous class, even in the previous question. Just there are 3: transmitter, communication channel, and the receiver. But also you are told to explain the advantage of using optical fiber systems and coaxial cable system in telecommunication process. I think this question its answer is found in telecommunication part 4. In space communication, I explained this question in a good fashion. I think you will be able to understand it and come back to answer this question. So another, it was Nectar 2015. Nectar 2015, paper 1. In Nectar 2015, paper 1, you were asked Give one advantage of frequency modulation as compared to amplitude modulation. I think this question I've already explained. I said it is noiseless reception, but also good audio quality, efficiency of operation, and other advantages. Go back to our previous class and you will be able to answer this question. So Roman 2, you were asked to explain briefly the importance of bandwidth of an amplitude modulated signal. Go back for a note C. This question is answered. 13B, Roman 1, state the function of a modulator in radios. I said modulator simply is for doing superimposition of a high energy carrier wave to a signal wave. Sketch a block code diagram to show the general plan of any communication system. I think in the previous class, I think it is telecommunication part 1, I explained the block diagram of any communication system. So number 13C, the amplitude modulated AM broadcasts band ranges from 450 to 1200 kHz. Each station modulates with audio frequency up to 5.5 kHz, determines the bandwidth needed for each station and the total bandwidth available. This question I've already solved its idea, so you can go back to our previous class and you can come back and solve this question. Nectar 2014 paper 1, number 13A, give the meaning of the following terms. Bandwidths, go back and read our previous class. Roman 2, amplitude modulated carrier wave, I already explained, is the previous class. B, what is the purpose of amplifiers? This question is very, very common. I've already explained the terminologies. Sketch a frequency spectrum of 1,500 meter radio waves modulated by a 4 kHz audio signal. I've already explained how to draw the frequency spectrum curve. C, listed down 2 advantages of digital signal over analog signals. This question will be explained in the part of digital electronics. 012, a carrier frequency of 800 kHz. This question I've already calculated it. I've already explained this question in the example number 2, I think. Okay. So Nectar 2013 paper 1, question B, Roman 1. Electrical properties of the atmosphere are significantly exhibited in the ionosphere. What is the layer composed of, and what do you think is the origin of such constraint? Simply, the layer is composed of electrons and free ions. I already explained. So the origin of the electron and the free ions are from the UV radiations, from the X-rays, from the cosmic rays. Those are the source of the ions and free electron. Mention 2 uses of the ionosphere. I explained 2 applications of ionosphere. I said the first one is to protect the living organism from the harmful UV radiations, but the second one is to prevent us from getting skin cancer. C, briefly explain why long distance radio broadcasts make use of short wave bands. So this question, I think I've answered this question here. Long distance radio broadcasts utilize shortwave band because this frequency, typically between 3 MHz to 30 MHz, are capable of being reflected by the ionosphere. I told you, the ionosphere cannot reflect back the signals with high frequency. So signals with high frequency can easily penetrate. So you must use shortwave bands because they can be reflected by the ionosphere. As we know, the ionosphere is used like a mirror to reflect back the transmitted signals to the receiver. And the answers of the other questions I already explained here. Okay. So I have some other questions. You can pass through them here. You can copy the questions because they appear in different examinations. So you can copy the questions, and then here are the answers. There are so many questions in telecommunication. I can't cover all the questions in this class. So you can go through the questions, and there are answers in different books. You can look for them. So up to here, this one is the end of telecommunication topic. So the end of telecommunication subtopic is the beginning of the new subtopic. Get in touch with this YouTube channel, and I hope you're going to benefit a lot. Don't forget to subscribe, like, and comment. It will be a big support to me.